Okay, this PowerPoint is continuing our discussion about modern atomic physics, and we're going to talk about photons and energy associated with photons. So, the energy of a photon, a single photon, can be represented as E is equal to hf. E is the energy in joules. H is Planck's constant, 6.6 times 10 to the negative 34, and F is the frequency in hertz. Now, off to the right is how the Regents reference table writes it. E photon is equal to hf. And if you don't know the frequency, if you know the wavelength, you can use the other version of the formula. E is equal to hc over lambda, where c is the speed of light, 3 times 10 to the 8th meters per second. So here I'm showing the same formula, and I'm also showing a representation of the electromagnetic spectrum. So E, energy in joules, is equal to h, Planck's constant, times the frequency in hertz. And sometimes you have to look at the table to get the frequency. So although this chart doesn't have any numbers, for example, I might ask you, well, what's the energy associated with 1 photon of a microwave? Well, you'd go to the chart, you'd look up what the value is for the frequency of the microwave, put it into the formula, so you'd multiply it by Planck's constant. That would give you the energy in joules. And yeah, just a little bit of review about the electromagnetic spectrum. As you move towards the left, you have a higher frequency and more energy. As you move to the right, you have a lower frequency and less energy. So if I asked what has more energy, X-rays or microwaves, the answer is X-rays. And you can see, although there's no numbers, there's a graphic above X-ray. It shows that the wave crests are very close together, means high frequency, and the waves are very small. That means a low wavelength, small wavelength. As I look at microwave, the wave crests are further apart. That means lower frequency, and the wave looks bigger. So that means larger wavelength. If I asked you what had more energy, blue light or red light, the answer would be blue, because blue is further to the left in this graphic. So I didn't show the chart here, but I asked, what is the energy associated with a photon traveling as an FM radio wave? So you'd go to the chart, you look up FM radio waves, and you see that the frequency is 1 times 10 to the 8th hertz. We put that into the formula, E is equal to hf, and we get an answer of 6.6 times 10 to the negative 24th joules, which is a really, really small amount of energy. But we're talking about 1 photon. I mean, that actual radio wave is billions and billions of photons. So 1 photon has a real small amount of energy associated with it. And we get to Einstein's famous equation, E is equal to mc squared. So Einstein realized there was a relationship between energy and mass. E is the energy in joules, m is the mass in kilograms, and c is the speed of light, 3 times 10 to the 8th meters per second squared. Where this takes place is in nuclear reactions. So in atomic explosions and nuclear power plants and radioactive decay, this is where we have mass turning into energy. So how much energy is stored in 52 kilograms of a substance, or how much energy would be released if we converted 52 kilograms totally into energy? We use E is equal to mc squared. We put in 52 kilograms and the speed of light, and we get 4.6 times 10 to the 18th joules, which is a huge, huge number. So on the worksheet, I ask you to convert from wavelength to frequency, and this is the way that we do it. Remember the wave formula, V is equal to F lambda. The speed of a wave is equal to the frequency times the wavelength. If you remember in class, we stretched that one spring the length of the classroom, and we talked about this formula. Well, when it comes to electromagnetic radiation, we can take the same formula and we can put C in place of V because C is the speed of light. All light, different colors, and microwaves and gamma rays, they all travel at 3 times 10 to the 8th meters per second in a vacuum. So I can take that formula, put C into it in place of V, and I can use that to convert frequency to wavelength and back. The formula, again, E is equal to HF. On the worksheet, I also ask you to convert between energy and frequency. So you're going to use this formula. And when you use this formula, the energy is in joules. So on the worksheet, I have a problem where the energy is in electron volts. And so you're going to have to use the conversion. 1 electron volt is equal to 1.602 times 10 to the negative 19th joules. So I have an example of that. This example does the conversion all in one step, but you could do it in separate steps as well. So let's take a look at it. At the peak of the sun's radiation spectrum, each photon carries an energy of about 2.7 electron volts. What is the frequency of this light? So what do we know? We know the energy, 2.7 electron volts, and Planck's constant, 6.6 times 10 to the negative 34th, and we're looking for the frequency. So we're going to use the formula E is equal to HF. It says use the equation for energy of a light quantum and isolate frequency. Isolate frequency just means solve the formula for F. So E is equal to HF. If I divide both sides by H, I get frequency is equal to energy divided by Planck's constant. So I substitute in. For energy, I put the 2.7 electron volts, but I also have to multiply it by our conversion factor, 1.6 times 10 to the negative 19th. And then I divide that by Planck's constant, 6.6 times 10 to the negative 34, and I get the answer 6.5 times 10 to the 14th hertz. So please look at this example when you attempt the similar problem on the worksheet. Energy and mass graph question. Which graph best represents the relationship between energy and mass in the mass-energy equation? And I wrote the equation up there, E is equal to mc squared. Well, it might be tempting to choose number 2 because our formula has a square in it, so we might think it's a exponential relationship, but that's incorrect. The correct answer is number 1, because we want the relationship between energy and mass, and it's not mass that's being squared, it's c, the speed of light, that's being squared. So the relationship between energy and mass is actually linear, and I'm showing that here. Energy on the y-axis and mass on the x-axis. It's a linear relationship because E is directly proportional to m, and the slope of that line would be the speed of light squared, would be c squared. Likewise, we can do the same thing with energy and frequency. Recall the formula is E is equal to HF. So energy on the y-axis and frequency on the x-axis is a direct relationship, and the slope would be h, or Planck's constant. So I want to talk about the photoelectric effect. I mentioned it in class before when we talked about light and Snell's law. But the photoelectric effect is what proves that light is a particle. Now, light is both a wave and a particle. We prove that light is a wave with constructive and destructive interference. And we prove that light is a particle with this photoelectric effect. So what is the photoelectric effect? Well, the graphic on the left shows light represented as red, the red waves, hitting this substance, and electrons are being emitted. So I wrote, when light, red waves of a known frequency hits a material, electrons are given off with specific amounts of energy. So yeah, photosensitive materials like to give off electrons when you shine light on them. So the picture on the right, we have this apparatus here where we're shining light or some sort of electromagnetic radiation on this plate. The plate is inside a vacuum tube and it's giving off electrons. We can then measure the current in the wire and determine how much energy the electrons have. And when we do this experiment, we see that the electrons always have specific amounts of energy. So that means that the light must have specific amounts of energy. So that means the light is coming in small packets of energy. That means the light is comprised of particles. So what you need to remember is that the photoelectric effect proves that light is quantized. It proves that light is made up of particles. And we call those particles photons. And the last thing I want to talk about is something called Compton scattering. And I think this is kind of interesting. When we see an object that has color, like something that's green, it's because the light, light in the room or light from the sun, bounces off the object and then hits our eye. And if the thing appears to be green, what's happening is the white light, which is all the colors, hits the object, and only the green is bouncing back to our eye. The other colors are being absorbed by that object. So what happens is, I wrote here in the first paragraph, when light hits an atom and bounces off, this is how we see things. The atom absorbs the photon, excites an electron, and emits a photon. So when something has a green color, that object is absorbing all the white light, but it's only bouncing the green back. And what color it bounces back has to do with the electrons inside the atoms of that object. So we can think of it as atoms absorbing photons and then giving photons off again. And in another lecture, I think next Monday, I'm going to talk about how that works. But this process, we can also think of it as photons and electrons colliding with each other. And we call that Compton scattering. So the picture to the left is showing a incoming photon, an incident photon. That's the red arrow coming from the left. It then hits an electron. Electron is the purple circle. The electron is then scattered. So the electron is then excited and then it gets some energy and it moves. And the photon bounces off as well. And when it bounces off, it has less energy because it gave some of its energy to the electron. So remember, lower energy means lower frequency. So that photon lost energy, so it now has a lower frequency. Lower frequency means larger wavelength. So the wavelength of the photon is larger. So in the middle paragraph I wrote, we can also describe this as a photon and electron collision. Then the bottom paragraph, the frequency of the scattered photon is always less, and the wavelength of the scattered photon is always more than the incident photon because the photon has lost energy to the collision. So what do you need to know about Compton scattering? You need to know it's a collision between a photon and an electron. You need to know that the electron gains energy. You need to know that the photon loses energy. You need to know that the photon wavelength is greater and the photon frequency is less. Okay, so please try the worksheet that goes with this lecture. And then I will also have a solution video that I'll put up as well.